On the morning of December 2nd, 2025, a subtle transformation was captured. Not by NASA, not by the European Southern Observatory, but by a network of independent telescopes watching 3I Atlas from Earth. Its shape had shifted, not fractured like a comet, not broken apart from heat, but morphed, cleanly, symmetrically and slowly and in real time. It happened as the object entered a new observational window. The outer edges that once appeared blurred and asymmetrical, now resolved into a sharp, oscillating boundary, not expanding outward chaotically, but folding inward, almost breathing. For weeks, 3I Atlas had defied comet logic. No chaotic outgassing, no predictable thermal response, just rhythmic pulses, synchronization anomalies, and energy mismatches. Before we begin, let me know where you're watching from and what exact time it is for you right now. In the early observations of 3I Atlas, it was easy to dismiss the object as just another interstellar comet. A slightly odd one, perhaps, but nothing extraordinary. Early imagery from wide-field ground telescopes showed the familiar traits: a soft glow, an indistinct halo, and the expected outward haze of material sublimating off an icy nucleus. To the untrained eye, it was a typical dirty snowball drifting through sunlight. But that illusion didn't last long. Within days of its first detailed tracking in late October, researchers began to note inconsistencies in its coma structure. Instead of chaotic jets and dust sprays, high magnification images revealed something static, an outline that was far too sharp to be explained by gas diffusion. Spectral filters failed to show any wide emission bands commonly associated with large-scale outgassing. In fact, what surrounded the core wasn't a dust cloud at all. It was something else, something more structured, and by December the 2nd, that structure became impossible to ignore. Multiple observatories reported that the light envelope around 3I Atlas had narrowed dramatically. At first, it seemed like a decrease in activity. Maybe the object was running out of volatiles, but then the brightness stabilized. More than that, it became geometrically consistent. The halo wasn't dispersing randomly anymore. It was concentrating, following contour lines around the body that suggested not expansion but definition. From Chile to South Africa, telescopes using polarized filters recorded what looked like edge definition, linear zones of contrast that shouldn't appear in any naturally diffused dust field. These ridges didn't rotate or fade like chaotic ejections. They remained locked in place, slowly morphing in unison as if they were surface-bound features adjusting orientation. By this point, the dust cloud explanation had broken down. Comets do not become more defined the closer they get to sunlight. They shed, they scatter, they degrade. But 3I Atlas was moving in the opposite direction, refining, not collapsing. That same night, the solar orbiter captured imagery that was quietly shared among scientific circles. Using its heliospheric imager, the probe caught a moment of silhouette, 3I Atlas, against the faint backdrop of solar haze. What it showed was remarkable. The outline of the object wasn't spherical, it wasn't even irregular, it was segmented. 3 lobes, slightly offset but joined. A trilobed form, faintly visible but distinct. That configuration has only one analogue in space science: structured composites. We've seen this with certain metallic asteroids, where gravity joins together chunks of material in a stable shape. But those are jagged, fragmentary. This was smooth. The light curve modulation followed a consistent rhythm across all 3 segments. When one edge flared, the others echoed it seconds later, like a wave running through a flexible frame. This was no dust cloud. Spectral analysis from the James Webb Space Telescope further deepened the mystery. Mid-infrared bands that should have been saturated with thermal radiation from outgassed particles were flat. Instead, narrow absorption lines appeared, suggesting that the light wasn't just bouncing off particulate matter, but interacting with a denser surface beneath. A surface that was cooling in sync with the object's shape change. Several researchers compared the transition to watching a jellyfish retract its bell. A luminous field drawing inward, not from collapse but from control. And like any organic contraction, the shift occurred gradually, observable across hours, not seconds. There was no explosive release, no flare, just an elegant reconfiguration. What had begun as a diffuse glow, what science initially labelled a cometary coma, was now gone, replaced by a coherent structure with angular resolution, thermal boundaries, and synchronized modulation. This was no longer a cloud, it was a form, and forms have purpose. At exactly 0411 UTC on the morning of December 2, 2025, a small telescope network in northern Chile registered something unexpected. The object catalogued as 3I Atlas, a known interstellar visitor already steeped in anomalies, had changed. Not in brightness, not in trajectory, but in form. Its outer visual signature no longer resembled a traditional coma. Instead, what emerged was a clean shift in shape. Geometric, symmetric, and unmistakably intentional in its structure. What had once appeared as a fuzzy, diffuse comet-like halo now resolved into a boundary. The edge of the object became sharp, not in the way one expects from fragmentation, but as if something internal had reoriented. Adaptive optics caught what appeared to be an undulation, subtle, timed, and phase-locked to the pulse frequency recorded in the days prior. The object wasn't collapsing, it wasn't shedding mass, it was tightening. Telescopes in Hawaii and La Palma confirmed the observation within minutes. What they saw matched precisely. The edges of the light-emitting region were no longer irregular. They had stabilized into a shell-like formation that fluctuated in a smooth oscillation every 9 minutes, matching the documented light pulse cycle from November. It was the same rhythm, but now it wasn't just light. It was structural. This was not the behavior of a dust-rich comet losing cohesion near solar heat. It looked more like controlled contraction. And that distinction matters, because for the past 2 months, 3I Atlas has already exhibited patterns that don't conform to known cometary models: reflected light with phase-locked polarization, ultraviolet pulses without corresponding heat, and a non-gravitational acceleration aligned with solar eruptions. But this morphing event changes the stakes entirely. The data coming in from the solar orbiter made the picture even stranger. Instruments on board recorded a tightening in the object's outer infrared emission ring, a phenomenon that suggested not only structural change, but internal redistribution of temperature. The thermal gradient was shifting inward. A cooling core had begun to contract, while the outer shell displayed sudden brightness stabilization, completely the opposite of what a body undergoing heat stress or sublimation would show. From a physics standpoint, the morphing observed on December 2nd broke 3 core expectations. First, the symmetry. Objects under solar radiation rarely shift uniformly. They tumble, deform, and fragment chaotically. Not so here. The transition was smooth. Second, the pacing. The oscillation was matched in period to the 9-minute emission pulses previously detected, suggesting a feedback mechanism, not a random break. Third, the directionality. Rather than expanding due to thermal load, the object's energy signature suggested a gradual retraction of its luminous outer field. By midday, the James Webb Space Telescope had contributed confirmation in the form of layered diffraction analysis. The diffraction ring around 3I Atlas had narrowed, not because of a drop in energy, but because the emitting region had physically contracted. The shell radius was now smaller by an estimated 3.4% compared to just 36 hours prior, and still, no debris, no tails, no jets, just shape change, clean and controlled. The term morphing entered the internal logs by afternoon. It wasn't chosen lightly. Comets don't morph, they disintegrate, they break. What we were witnessing was different, a transformation without material loss, a visual tightening that obeyed not chaos but rhythm. At Mount Lemmon, researchers compared this structural shift to adaptive regulation systems seen in orbital spacecraft. The shape change seemed to correlate with environmental inputs, solar flux, magnetic field density, and most notably observation timing. When Earth-based observatories aligned with peak pulse output, the shape change appeared most pronounced. Whatever is happening inside 3I Atlas began visibly unfolding on December 2nd. It did not explode. It did not scatter. It evolved. And that may be the most unnatural thing we've seen yet. In the early observations of 3I Atlas, it was easy to dismiss the object as just another interstellar comet. A slightly odd one, perhaps, but nothing extraordinary. Early imagery from wide-field ground telescopes showed the familiar traits: a soft glow, an indistinct halo, and the expected outward haze of material sublimating off an icy nucleus. To the untrained eye, It was a typical dirty snowball drifting through sunlight. But that illusion didn't last long. Within days of its first detailed tracking in late October, researchers began to note inconsistencies in its coma structure. Instead of chaotic jets and dust sprays, high magnification images revealed something static, an outline that was far too sharp to be explained by gas diffusion. Spectral filters failed to show any wide emission bands commonly associated with large-scale outgassing. In fact, what surrounded the core wasn't a dust cloud at all. It was something else, something more structured. And by December 2nd, that structure became impossible to ignore. Multiple observatories reported that the light envelope around 3I Atlas had narrowed dramatically. At first, it seemed like a decrease in activity. Maybe the object was running out of volatiles. But then the brightness stabilized. More than that, it became geometrically consistent. The halo wasn't dispersing randomly anymore. It was concentrating, following contour lines around the body that suggested not expansion, but definition. From Chile to South Africa, telescopes using polarized filters recorded what looked like edge definition, linear zones of contrast that shouldn't appear in any naturally diffused dust field. These ridges didn't rotate or fade like chaotic ejections. They remained locked in place, slowly morphing in unison, as if they were surface-bound features adjusting orientation. By this point, the dust cloud explanation had broken down. Comets do not become more defined the closer they get to sunlight. They shed, they scatter, they degrade. But 3I Atlas was moving in the opposite direction, refining, not collapsing. That same night, the solar orbiter captured imagery that was quietly shared among scientific circles. Using its heliospheric imager, the probe caught a moment of silhouette. 3I Atlas against the faint backdrop of solar haze. What it showed was remarkable. The outline of the object wasn't spherical. It wasn't even irregular. It was segmented. 3 lobes, slightly offset but joined. A trilobed form, faintly visible but distinct. That configuration has only one analogue in space science: structured composites. We've seen this with certain metallic asteroids, where gravity joins together chunks of material in a stable shape. But those are jagged, fragmentary. This was smooth. The light curve modulation followed a consistent rhythm across all 3 segments. When one edge flared, the others echoed it seconds later, like a wave running through a flexible frame. This was no dust cloud. Spectral analysis from the James Webb Space Telescope further deepened the mystery. Mid-infrared bands that should have been saturated with thermal radiation from outgassed particles were flat. Instead, narrow absorption lines appeared, suggesting that the light wasn't just bouncing off particulate matter, but interacting with a denser surface beneath, a surface that was cooling in sync with the object's shape change. Several researchers compared the transition to watching a jellyfish retract its bell, a luminous field drawing inward, not from collapse, but from control. And like any organic contraction, the shift occurred gradually, observable across hours, not seconds. There was no explosive release, no flare, just an elegant reconfiguration. What had begun as a diffuse glow, what science initially labelled a cometary coma, was now gone, replaced by a coherent structure with angular resolution, thermal boundaries and synchronized modulation. This was no longer a cloud, it was a form, and forms have purpose. As of the early hours of December 2nd, 2025, 3I Atlas no longer behaves like a passive interstellar object drifting through the solar system. Its form, previously ambiguous and clouded by thermal haze, is now evolving in a way that suggests not randomness, but precision. Specifically, phase precision. What does that mean? In astrophysical terms, phase refers to a point in a repeating cycle, usually light, motion, or rotation. It's how we track pulsars, binary stars, or thermal waves. But with 3I Atlas, the phase is showing up in something else entirely. Its morphology, its shape. Over the last 3 observational windows, scientists have recorded a pattern that can't be accidental. The object's outline is not just changing, it's changing in rhythm. Every 9 minutes, a subtle structural shift is observed. First the outer glow tightens, then the thermal distribution realigns, and finally the visual edge sharpens before relaxing again. The cycle then restarts, cleanly and consistently, without observable deviation. This is not the behaviour of natural cometary material. There is no known physics model, in which random outgassing can trigger synchronized mechanical deformations across an object of this size, especially not with repeatable intervals. Yet that is precisely what the global data now confirms. Phase-locked evolution is rare in space. The only objects that exhibit it consistently are artificial satellites, solar sails, and active probes, adjusting orientation, or load distribution. But 3I Atlas is not of Earth origin. It arrived from interstellar space with a hyperbolic trajectory and no evidence of control systems, at least not visible ones, and yet its structure evolves like a machine under command. At the European Southern Observatory, a team of astrophysicists studying light curve data over a 72-hour window found something extraordinary. The shape changes are not just periodic, they're predictively synchronized with solar radiation pressure. When the solar wind peaks, the phase begins. When it dips, the object remains static. It's as if 3I Atlas is responding to solar input not passively, like dust or gas, but actively, as if adjusting based on external conditions with mechanical timing. This same phenomenon was echoed in the data from NASA's Parker Solar Probe, which picked up corresponding field perturbations during each shape change interval. These perturbations matched the object's timing, even though no ionization signature was present. That means the object's form is affecting local electromagnetic conditions without shedding mass. Another clear break from comet behavior. Further analysis from the Lunar and Planetary Laboratory in Arizona modeled these oscillations against all known rotational instabilities. The conclusion was unanimous. The object isn't spinning fast enough to cause such deformation, nor is there enough thermal lag to justify cyclical flexing from solar heating. Which leaves us with the most unsettling explanation. The shape of 3I Atlas is changing on a timed loop, not due to physics, but due to feedback. Imagine a system that checks the intensity of sunlight, then adjusts its geometry to either reflect, absorb, or stabilize radiation across its surface. That's how satellites with dynamic shielding operate. It's how thermal cloaking experiments are being developed in terrestrial labs. And it's what 3I Atlas appears to be doing at interplanetary scale. Its pulse isn't just energy, it's timing, a heartbeat, and the changes in shape are occurring at precisely the same intervals as its most coherent optical pulses, down to the millisecond. In short, the object isn't just pulsing light, it's pulsing structure. We don't know if this is a natural property of unknown interstellar material or the behavior of something designed, but one thing is now certain. The changes we're seeing are not chaotic, they're calibrated, and with every new phase, the structure becomes more defined. By December 2nd, 2025, something quietly but critically shifted in the way scientists observed 3I Atlas. Not in its light curve, not in its trajectory, but in its thermal footprint, a detail easily overlooked by the casual observer, but deeply troubling to anyone studying cometary behavior. Because now, the thermographic outline of 3I Atlas no longer matches its visible coma. That's not a poetic way of saying it looks different in infrared. That's a literal observation. The heat signature and the visual shape are no longer aligned. In traditional comets, the coma, essentially the luminous halo of dust and gas, is a direct product of sublimation. The surface heats, the ice turns to vapor, and a cloud forms around the object. The shape and size of the coma almost always match the areas that are thermally active. You can map the hot zones and trace their diffusion into visible form, but not with 3I Atlas, not anymore. Data from the James Webb Space Telescope's MIRI, mid-infrared instrument, showed something no comet has ever exhibited at this distance from the Sun, a detached thermal boundary. Infrared overlays taken between 0330 and 0445 UTC show a smooth elliptical heat signature surrounding the object. But when that signature is compared with high-resolution visible light images from the solar orbiter and La Palma, the shapes diverge. The optical coma is larger, wider by several hundred kilometers in all directions, and asymmetrical, shaped like a faint disk flaring toward one edge. The heat signature, however, is tight, centralized, and symmetrically balanced, forming a clean oval without directional distortion. This thermal mismatch is unprecedented. To make matters more complicated, the peak heat source isn't where it should be. In all known comets, solar heating produces maximum infrared output on the sun-facing hemisphere. But 3I Atlas is now showing thermal centralization, a uniform heat ring surrounding the nucleus rather than a hotspot. Even stranger, the visual brightness is skewed toward the solar vector, while the infrared emission remains centered. In simpler terms, the object is visually reacting to sunlight, but not thermally responding to it in any way that makes sense. So what explains this? The first hypothesis was lag, maybe the heat hadn't caught up yet, but that was ruled out within hours when time-lapse thermographic overlays showed no shift. The infrared profile held firm even as the object passed through varying solar angles. Then came the idea of shielding. Could 3i Atlas be coated in material that deflects or suppresses infrared energy? That would be bizarre but plausible, until radiometric measurements showed that the total emitted energy was within normal ranges. The object isn't deflecting heat, it's just redistributing it internally. Several models now suggest that the outer layer of 3i Atlas behaves like a thermal lens, bending heat inwards, not outwards. This would explain why the hot zone is evenly distributed instead of sun-facing. But for that to be true, the surface would have to possess extremely unusual properties, like negative thermal conductivity, something not observed in any natural comet or asteroid. At the University of Oslo's Magnetoplasma Lab, one research group proposed that a surrounding ionized field could be acting like an electromagnetic shell, filtering different wavelengths of energy in and out at will. This could create the illusion of mismatch, when in fact both visual and thermal responses are being modulated separately. That's not typical behavior, that's system-level control. And here's the final piece. When mapped in detail, the infrared outline of 3i Atlas forms a rotating torus, a donut-shaped pattern that spins slowly on a 9-minute interval, perfectly synced with the object's pulse cycle. The coma no longer tells us what the object is doing. The heat does, and the heat is acting like it's been engineered. At 0512 UTC on December 2nd, 2025, the Mount Stromlo Observatory in Australia reported a strange atmospheric reading, not within Earth's atmosphere but between Earth and 3i Atlas. A series of fast-moving shadow bands, dark, wave-like fluctuations in light intensity, were recorded near the optical edge of the object. At first, this was assumed to be an imaging artifact or high-altitude turbulence, but within 18 minutes, 4 more observatories confirmed the same phenomenon from entirely different angles, including the Canary Islands, Chile, and Japan. Each site observed something nearly identical. Rapid, striped oscillations in the region just beyond the coma, too structured to be random, too synchronized to be coincidence. They weren't comet jets, they weren't light distortions caused by the sun, they were shadows, and they were moving in waves. So what exactly are oscillating shadow bands and why do they matter? On Earth, this effect is extremely rare. It's occasionally seen during total solar eclipses, where sunlight passing through atmospheric turbulence creates flickering bands across the ground in the seconds before totality. These patterns are chaotic, faint, and random. But what was seen near 3i Atlas was the opposite. Clean, evenly spaced and locked to a cycle. Space-based telescopes confirmed the directionality of the pattern. The shadows weren't being cast from Earth's atmosphere or passing clouds. They were emanating from the vicinity of 3i Atlas itself, trailing outward in a rippling field that extended several hundred kilometers beyond the visible boundary of the object. Each band repeated every 42 seconds, with a measurable speed of propagation consistent with a wavefront, not random scattering. This introduces 2 immediate problems. First, comets do not cast structured shadows. Their comas are diffuse, their tails are chaotic, their light distribution is isotropic, meaning it spreads out in all directions and blurs at the edges. There is no known mechanism that would produce regular shadow oscillations from dust particles, ion tails, or outgassing jets. Second, the bands weren't cast on solid surfaces. They were measured in free space, as modulations in light intensity detected by synchronized high frame rate photometers. In other words, the bands weren't shadows on land or clouds. They were dynamic absences of light in the path of telescopic vision, as if the vacuum itself was being rippled. The working hypothesis from the European Space Agency's optics team is that these shadow bands represent coherent light interference, an optical phenomenon in which overlapping waveforms cancel each other out in specific regions. That would require 2 conditions: a consistent high-frequency light source, an environment where light is being manipulated deliberately, possibly refracted or diffracted through a structured medium, And that brings us to the object itself. If 3i Atlas is surrounded by a shell or field capable of bending or splitting light, then we would expect to see interference patterns under the right angles. But the regularity of the wavefronts, each 42 seconds apart, each identical in spacing and shape, points to more than just passive interference. Several labs now believe we're witnessing a form of optical modulation, a timed rhythmic change in the object's light output, creating interference with incoming solar radiation and projecting ripple-like shadows outward. More simply, the object may be pulsing light deliberately, and the surrounding field is shaping that light into structured dark bands. At the University of Tokyo's Photonics department, researchers overlaid this data with the known pulse frequency of 3i Atlas, previously measured at every 9 minutes. The shadow bands now appear to be a secondary harmonic, a faster oscillation embedded within the larger structural pulse. This links the event back to the object's core, not just in light, but in control. And here's the most unsettling part. As 3i Atlas continues to morph and pulse, the shadow bands are becoming more defined, as if the system creating them is stabilizing, tuning itself, or focusing. What began as a subtle flicker in peripheral vision is now one of the clearest signs that 3i Atlas isn't just interacting with light, it's sculpting it. In the hours following the December 2nd observation window, researchers across multiple time zones began to notice something deeply unusual in the light curve data coming from 3i Atlas. Not a fluctuation in brightness, not an energy spike, but a delay, a time-staggered pattern in how different parts of the object reflected light. Under normal conditions, light curves from a rotating body in space should sync uniformly. As the object spins, its surfaces reflect light based on angle, composition, and solar exposure. If there's a pulse, thermal, photonic, or structural, it typically radiates outward symmetrically from the source. But with 3i Atlas, that rule no longer applies. What scientists recorded instead was phase staggering, a measurable delay in how brightness evolved across different sectors of the object. When one side brightened, the other followed, not simultaneously, but several seconds later. This wasn't due to viewing angle. It was recorded by multiple observatories from widely separated geographic locations, and each dataset confirmed the same sequence. Light originating from the forward edge of the object appeared first, followed by a ripple of brightness across the surface, reaching the rear edge 12 to 15 seconds later. Why does this matter? Because staggered light curves suggest one thing: structural flexing. Something is moving, slowly, deliberately, across the body of 3i Atlas. And whatever is, moving isn't random, it's coherent. Imagine a thin sheet being gently bent from one side to another. The bend doesn't happen all at once, it propagates like a wave, with light catching on the changing angles as each section flexes. At the European Southern Observatory, analysts described this effect as a photonic sweep, a dynamic, asymmetric reflection likely caused by an object deforming in a timed pattern. Their analysis revealed that the peak brightness across sectors occurred in a sinusoidal wave, almost identical to those found in engineered mechanical structures undergoing stress or controlled shape change. Even more striking, the timing of the brightness wave was locked to the now familiar 9-minute pulse interval. Each pulse was followed by this sweeping flex pattern, starting on the object's leading edge, travelling across the body, and terminating on the opposite side before resetting again. This means two things. First, the object is not static. Second, its structural changes are happening from within, not from external forces like solar wind or gravity. Comets do not flex this way. They fragment, they tumble. When subjected to heat or radiation, their surfaces flake off, explosively or unpredictably. Nothing about 3i Atlas follows this path. Instead, its light emission suggests elastic motion, as if layers of its body are capable of controlled reorientation. Data from the Parker Solar Probe supports this. Instruments detected a faint electromagnetic ripple propagating alongside the optical pulse, suggesting that the flex may not be purely mechanical. It could be tied to magnetostrictive behavior, a material property where shape changes in response to magnetic fields. That kind of behavior has no precedent in natural comets. It does, however, appear in advanced metamaterials and engineered alloys. At the University of Zurich, a materials science team modelled the staggered light curve as if it came from a thin, flexible hull segmented into plates. Their simulation matched the observational data almost exactly when they introduced internal actuators, devices that flex segments in response to periodic electrical impulses. Now, no one is saying 3i Atlas has mechanical actuators inside, but the simulation raises a disturbing possibility that this interstellar object is structured to flex, and it's doing so on a timer. What we're seeing may not be erosion. It may be alignment, a recalibration of its surface in preparation for the next phase of its missional path. The light curve isn't just showing us brightness, it's revealing a heartbeat of motion. At 0603 UTC on December 2nd, 2025, a sequence of near-infrared NIR images taken by the Infrared Telescope Facility, IRTF, in Hawaii, revealed something that no one expected from an interstellar object, especially not one already known for thermal anomalies, structural pulses, and phase-locked morphing. For a duration lasting just over 18 seconds, portions of 3i Atlas appeared to become semi-transparent. The infrared frames, captured in rapid succession at high temporal resolution, showed a faint but measurable transmission of light through the outer edge of the object. In other words, a narrow band of near-infrared wavelengths that had previously reflected or scattered off the surface now passed through it. What had been a solid emitter one moment suddenly allowed light to bleed beyond its usual thermal contour. This transparency was not constant. It flickered, appearing briefly, vanishing, then reappearing again 9 minutes later, precisely synchronized with the object's known pulse interval. The phenomenon immediately triggered cross-verification. Within hours, independent teams at La Palma Observatory and the Subaru telescope in Japan confirmed identical findings. Each detected a brief thinning in the thermal layer, localized to the object's forward-facing segment and locked to the exact same coordinates. The alignment across facilities eliminated any chance of it being a lensing effect, processing artifact, or sensor drift. So the question became clear: how does a solid body become temporarily transparent to infrared light? Natural comets, even those with hollow or fragmented cores, do not exhibit this behavior. Dust clouds can scatter light, ice can refract it, but neither can selectively turn transparent in the infrared spectrum, especially in a cyclical pattern. Transparency, especially in this band, implies material reconfiguration or active filtering. At the Max Planck Institute for Astronomy, a deep spectral analysis revealed that the transparency occurred specifically between 1.42 and 1.78 microns, a narrow band typically associated with water vapor absorption. Yet there was no increase in vapor output, no spectral spikes, no dust trail. The infrared window didn't open because something sublimated. It opened because the structure itself changed how it interacted with light. Several research teams now believe this is a manifestation of metamaterial behavior, a property seen in certain engineered compounds that can shift their refractive index dynamically. These materials are used in experimental cloaking systems and adaptive optics, allowing light to pass through under specific electrical or magnetic conditions. If that sounds like science fiction, you're not alone, but the evidence is stacking. The transparency events weren't diffuse. They were shaped, forming a symmetrical arc along the object's perimeter, like a lens activating and deactivating on a loop. The arc itself tracked with the same progression as the known structural flexing wave, suggesting the two phenomena are not separate but linked. The implications are unsettling, because if the object is becoming transparent on a timer, that means it's controlling how it's seen, and if it's doing that in response to internal cycles or solar conditions, then it's managing visibility. In other words, 3i Atlas may be revealing and concealing parts of itself rhythmically, like a signal, or like a system regulating heat, reflection, or external detection. One researcher at Caltech compared the effect to adaptive skin, a theoretical concept where spacecraft hulls change their optical properties depending on incoming light intensity or thermal conditions. That concept exists only on paper, on Earth. Yet 3i Atlas is doing something eerily similar in deep space without human design. And here's the most critical detail. During the transparency phase, background starlight was seen through the object, not refracted, not absorbed, passed through. Whatever 3i Atlas is, it is not entirely solid, not entirely stable, and certainly not passive. It's beginning to let light in, and for a few seconds at a time, it lets us see what's behind it. By the evening of December 2nd, 2025, optical scientists noticed something deeply irregular in one of the least discussed aspects of astrophysical imaging: diffraction patterns. Specifically, the diffraction signature along the outer edge of 3i Atlas, the subtle bending and scattering of light that occurs at the boundary where an object obstructs or redirects incoming photons, was no longer behaving as expected. In clean astrophysical terms, this was a phase boundary shift. But in practical terms, it meant this: the edge of the object was warping the light around it differently, over time and on a schedule. This realization didn't come from a single telescope. It emerged from a coordinated analysis between the Gran Telescopio Canarias, the European Southern Observatory, and the Parker Solar Probe. Each had logged thousands of frames throughout the day. But when they began overlaying sequential observations, a consistent anomaly appeared. The pattern of light bending at the object's edge was migrating, slowly but measurably. Under normal conditions, any object in space will produce a predictable diffraction pattern based on its shape, size, and surface interaction with incoming light. The sharper the edge, the cleaner the fringe. The fuzzier the edge, the more dispersed the ring. These signatures are static unless the object itself is rotating, fragmenting, or undergoing material changes. But in the case of 3i Atlas, the diffraction fringe was changing, not randomly, not chaotically, but in rhythm. Every 9 minutes, matching the known internal pulse frequency, the outer ring of scattered light would contract, becoming denser and tighter. Then, as the pulse faded, the ring would expand outward again, but with slightly altered geometry each time. Over the course of 3 hours, this created a progressive spiral, a rotating diffraction field that no natural comet has ever exhibited. The term now being used by optical physicists is edge rephasing. It describes how 3i Atlas appears to shift not just its structure or brightness, but the way it interrupts and redistributes light at its boundaries. This implies that the outer edge of the object isn't a fixed inert surface, it's a dynamic optical interface, possibly a thin electromagnetic or refractive shell. At NASA's Goddard Space Flight Center, scientists ran the numbers. To cause such consistent changes in diffraction shape, the outer layer of 3i Atlas would need to alter its effective refractive index by as much as 7% during each pulse cycle. That level of precision isn't seen in dusty atmospheres or gas halos. It requires structure, it requires timing, and it likely requires internal control. One of the most striking pieces of evidence came from data collected during a brief occultation event, when 3i Atlas passed in front of a background star field. The starlight, instead of simply dimming, split into bands as it passed near the object's limb. The result was a fringe pattern resembling what we see in Young's double-slit experiments, a hallmark of coherent light interference. This isn't how comets behave. This is how engineered materials behave, materials capable of interacting with light at a waveform level. Several theoretical models now suggest that the outer edge of 3i Atlas functions more like a variable diffraction grating than a dusty surface. That would mean it's capable of adjusting how incoming light bends around it, potentially to manage its own visibility, heat absorption, or external detectability. It raises the obvious but unsettling question: why would an interstellar object manipulate its edge diffraction pattern? There's no known natural benefit. There is, however, a functional reason for spacecraft, cloaking systems, and adaptive probes to control their diffraction profile, to minimize detectability or redirect energy. If this object is tuning its edge signature on purpose, then we're no longer talking about passive behavior. We're witnessing intentional interaction with the surrounding electromagnetic environment. And perhaps most remarkable of all, the diffraction ring, once diffuse and comet-like, is beginning to sharpen into a uniform optical boundary. It no longer looks like a comet. It looks like a silhouette, one that chooses when and how to be seen. By midday on December 2nd, 2025, headlines began speculating that 3i Atlas was undergoing some kind of disintegration. Mainstream outlets latched onto the idea that its changing shape, documented in infrared, visual and diffraction data, was a sign that the object was fragmenting like any large comet nearing the Sun. But when observatories and deep field arrays around the world searched for the telltale signatures of a breakup, there was nothing. No expanding dust field, no secondary trails, no lagging fragments, no shift in the object's centre of mass. This absence of debris is one of the clearest indicators that what's happening to 3i Atlas is not a natural cometary breakup. In fact, the lack of debris directly contradicts how fragile bodies behave when exposed to thermal and gravitational stress in interplanetary space. Let's start with the known behaviour of typical comets. As they approach the Sun, they heat up. Volatile ices begin to sublimate. Pressure builds inside their porous structures, often resulting in jets of gas, dust clouds, and eventually fragmentation. This is a chaotic process, with small to medium pieces flying off in irregular trajectories, leaving behind debris trails that remain detectable for weeks or even months. The Rosetta mission observed this firsthand with Comet 67P. Fragments separated and drifted visibly. In the case of Comet Eson, its dramatic disintegration near perihelion created a bloom of reflective particles, clearly visible in solar coronagraphs. And even distant interstellar visitors like 2i Borisov shed material as they entered the solar system. But 3i Atlas is doing none of that. Despite its shape visibly morphing and its boundaries oscillating, deep field instruments have detected no particulate field, even at distances as low as 10 kilometers from the object's center. High-sensitivity light scatter readings from the solar orbiter show no increased brightness in the object's wake, meaning no cloud of ice, dust, or gas. The James Webb Space Telescope, JWST, also conducted a focused sweep using its NIRCam, near-infrared camera, and MIRI, mid-infrared instrument. In all observational bands, no thermal hotspots or trailing fragments were found. Not even the spectral noise you'd expect from micron-sized particles was detected. This suggests something extraordinary. Whatever change 3i Atlas is undergoing, it is happening internally without mass loss. The structure is reconfiguring, not disintegrating. Dr. Lian Zhou, a solar system dynamics expert at the Chinese Academy of Sciences, called the behaviour physically elegant. Her team noted that the object's brightness curve remained tightly modulated, with no erratic jumps that would imply off-axis fragment ejection. In fact, the object's motion has remained remarkably stable. Its rotation period, orbital trajectory and light curves continue to show harmonic consistency. If anything, 3i Atlas appears to be stabilizing further, not deteriorating. One potential explanation being explored involves internal phase modulation, the idea that 3i Atlas is adjusting its own internal geometry, either through shape memory materials or controlled realignment of segments. These theoretical materials can undergo dramatic shape changes without fracturing and without shedding mass. This theory fits the data. The external morphology shifts, diffraction signatures evolve, but there is no mass trail to suggest damage. But perhaps the most compelling piece of evidence came from a phenomenon that should have appeared, but didn't. Between OLO 6U and 10 Haru UTC, Earth-based telescopes pass through the predicted debris shadow zone, an observational corridor where, had the object been shedding material, Earth-based sensors would have detected transit flickering or background dimming. Instead, telescopes recorded no anomalies, confirming that the space surrounding 3i Atlas is clean, controlled, and unpolluted by fallout. So what does this mean? It means that whatever 3i Atlas is doing, whether shifting, flexing, or transforming, it is doing so with a degree of control that no natural object has ever displayed. We are not witnessing destruction, we are witnessing coordination, and if no pieces are breaking off, maybe that's because the object was never built to fall apart. As December 2nd unfolded, yet another anomaly began to solidify in the multispectral data from ESA's solar orbiter, the Hubble Space Telescope, and two ultraviolet-capable instruments based in Antarctica and Chile. Each of them, working independently, confirmed a striking new pattern in the behaviour of 3i Atlas. Its ultraviolet reflectivity had become region-specific. In other words, only certain parts of the object were now reflecting ultraviolet light, while other sections remained conspicuously dark, completely non-reflective in the same wavelengths. This stands in stark contrast to natural cometary bodies, which generally exhibit a uniform UV reflectivity due to their dust halos and widespread volatile ices. Even as comets rotate, the scattering of ultraviolet photons tends to remain broad and diffuse, flickering slightly but never isolating into clean geometric patches of brightness. In this case, however, 3i Atlas is different, radically different. The change was first noticed in a 4.2-minute sweep performed by NASA's Swift Observatory. which detected 3 discrete zones of elevated UV albedo, one near the object's northern limb, a second on the trailing side, and a third at the centre, bordering what appears to be a symmetrically recessed cavity. These zones lit up only when the object passed through the 149 to 285 nanometer range, and only during the peak phase of its 9-minute pulse interval. Between those intervals, nothing. They went completely dark again. At first, some astronomers suspected this might be due to topographical shadowing, perhaps deep cavities reflecting UV light when hit at just the right angle. But further modelling eliminated this. The zones weren't shaped like craters or cliffs. They were flat, yet exhibited discrete angular reflectivity, consistent with tuned surface chemistry or structural alignment. More remarkably, the zones were stable in location, locked to coordinates on the object itself, not shifting with rotation as one would expect. This means that the material or structural orientation responsible for the UV reflection is embedded, not superficial. And more than that, it's responding to some internal clock or synchronization trigger. To make sense of this, researchers turned to a concept rarely applied in cometary science: anisotropic UV modulation, the ability of a surface to reflect ultraviolet light differently based on directionality, time, or field orientation. It's a concept explored in the development of adaptive military coatings and deep space sensor shielding, but not in naturally occurring rocks. The implication is clear. 3i Atlas is selectively controlling its UV signature, not as a byproduct of erosion, but as a function of design. This selective reflection might serve several purposes. One theory is that these regions are acting as thermal regulators, selectively reflecting high-energy photons to maintain a stable internal temperature. Another theory suggests they may be signal emitters, broadcasting brief UV pulses detectable across interstellar distances by systems tuned to those specific bands. A third, more speculative hypothesis comes from a research team at the SETI Institute, that these UV hotspots may function as a kind of modulated skin, opening and closing UV reflectivity windows as part of a non-radio communication system. If this were true, it would mean 3i Atlas is emitting directional UV bursts, potentially toward Earth, but also possibly toward other objects in space. What can't be dismissed is the consistency. These reflectivity zones repeat every 9 minutes. They persist in shape. They pulse with a mathematically regular interval. And most disturbingly, each hotspot has now been observed to rotate slightly in sync, not with the object's natural spin, but with an internal phase offset of 1.3 seconds, suggesting dynamic repositioning, as if the reflecting regions are recalibrating their angle toward some target. Comets do not do this. Natural bodies cannot do this. So the only remaining question is, what exactly is being emitted? What exactly is being avoided? And who, or what, is the intended recipient? Because if ultraviolet reflectivity is being modulated like a signal, then 3i Atlas is no longer just being observed. It may be observing back. By the late hours of December 2nd, 2025, a new layer of mystery began to form, this time not above or around 3i Atlas, but beneath its surface. Infrared and mid-infrared imaging captured by both James Webb Space Telescope, JWST, and the Very Large Telescope Interferometer, VLTI, in Chile, revealed that specific regions under the surface of 3i Atlas were exhibiting something highly unusual: localized cooling zones that weren't stable, but were moving, shifting, and repeating on a clock. This was not a case of uneven solar heating. It wasn't thermal loss from spinning exposure to the sun. It was something else entirely, a rotational pattern of internal cooling, synchronized with the same 9-minute pulse window that had already defined many of the object's observable behaviors. To understand why this is so significant, consider how natural celestial bodies handle heat. In comets or asteroids, internal heat tends to dissipate slowly and uniformly. The deeper beneath the surface, the more insulated the material becomes. Thermal inertia, especially in bodies with frozen cores, or porous interiors, means that subsurface temperature shifts are rare, gradual, and never patterned. Once a surface heats, it stays warm until far after its exposure ends. Once it cools, it does so passively. But with 3i Atlas, we are seeing something that flips this entire model. Subsurface cooling zones are activating in regular intervals and locations, without external triggers. Thermal maps produced using JWST's MIRI instrument show at least 4 distinct cold patches, each with a radius of roughly 300 to 500 meters, appearing just beneath the surface. These zones dip as much as 12 degrees Kelvin below the surrounding temperature, then warm back up again as if responding to an internal thermostat. What's even more alarming is how these zones shift. They don't rotate with the body. They migrate across fixed coordinates, sometimes moving laterally, other times vanishing entirely, only to reappear in a mirrored position minutes later. This behavior implies active thermal management, not diffusion, not decay, deliberate movement of energy. At the Max Planck Institute for Extraterrestrial Physics, researchers ran simulated thermal models using a range of internal compositions, from porous silicates to icy ammonia cores. None could reproduce the precise timing or rhythmic thermal cycling seen in the real observations. The only way to match the pattern was to introduce a hypothetical internal structure, possibly made of layered panels or channels, that could redirect or store heat on command. Think about that. An interstellar object, cooling and reheating itself on a schedule as if maintaining specific internal conditions. One hypothesis gaining traction is that these zones represent heat sinks, possibly part of a larger system designed to stabilize or protect something inside the object, perhaps a hollow compartment or energy source. In spacecraft design, heat sinks are used to absorb bursts of energy, preventing systems from overheating. The correlation here is uncanny. Another theory posits that the shifting cooling zones may be involved in a kind of stealth function, reducing thermal visibility in specific directions at certain times. That would explain why the cold regions are always opposite the solar vector and occasionally aligned with Earth's observational arc, as if minimizing their heat signature from our vantage point. Still, there's a third possibility, one that stems from biomimicry. In some biological organisms, rhythmic cooling is part of a life support mechanism, regulating core temperature based on stimulus or phase of activity. This idea is, of course, speculative, but it's worth noting that 3I Atlas is demonstrating adaptive thermal behavior unlike anything previously recorded in the history of observational astronomy. What remains consistent across all models is this: the object is responding from the inside out. It isn't being eroded, it isn't being destroyed, it's doing something, and every time one of these zones cools, a counterpart elsewhere on the object warms, perfectly balanced, as though redirecting thermal flow with intention. The more we watch it, the more it resembles a system, not a rock, not a comet, a regulated entity with internal processes that we are only beginning to decode. On the night of December 2nd, 2025, something happened that should be impossible under every current model of celestial mechanics and cometary behavior. For the first time since its detection, 3I Atlas was observed reflecting internal light, not sunlight from its surface, not scattered emissions from a dust halo, but light originating from within, bouncing off internal structures and escaping through narrow shifting windows in its body. And most critically, these internal reflections were recorded simultaneously from 3 separate locations on Earth, each hundreds of miles apart, each equipped with different equipment, and each witnessing the same impossible signal. The first detection came from the Mauna Kea observatories in Hawaii. Using a combination of adaptive optics and deep field image stacking, they observed a brief triangular glint emerge from the core of the object, lasting less than 2 seconds and moving not outward but laterally across the interior curvature of the object's silhouette. Within 90 seconds, a similar reflection, sharper this time, was observed from the Pic de Midi Observatory in the French Pyrenees. Despite atmospheric interference, the signal's path could be reconstructed. It followed a slightly curved path, as though bouncing off internal angles, exactly what you'd expect from mirrored surfaces or structural channels. And then came the third most undeniable confirmation, from the Siding Spring Observatory in Australia. There, under near-perfect visibility, a narrow light pulse was recorded exiting the body of 3I Atlas, not glowing, not scattering, but reflecting, like a beam escaping through a slit. Each of these observations was time-stamped and synced via atomic clock calibration. When compared side by side, a singular fact emerged. The angle and timing of each reflection matched a mirrored path inside a hypothetical hollow body. What does this mean? Let's step back. In standard comet models, light does not bounce through the interior. Comets are porous, opaque, and disordered. Their cores are full of frozen volatiles, carbon-rich rubble, and unstructured debris. There's no mechanism by which light could travel through the object, reflect off internal features, and exit again, especially not in repeatable angular patterns. But what was seen on December 2nd violates that expectation. These weren't flukes, they weren't cosmic rays. They were angular light deflections consistent with flat, smooth, possibly metallic surfaces. If this were a spacecraft or even a shell-like structure, these observations would make immediate sense. Light entered, struck an internal wall, and exited on a fixed trajectory. That's optical reflection, not diffusion. Optical physicists at Caltech and the Max Planck Institute began modeling this behavior using ray tracing algorithms. The simulations found that the only viable solution for all three reflection paths to exist simultaneously, at those specific timings and from those vantage points, was if the object contained at least two internal flat surfaces, angled at approximately 42 to 46 degrees, creating a prism-like effect. But here's the deeper implication. The light source was not external. Sunlight alone could not have entered those angles at that depth. The intensity and coherence of the beams implied they were either A. internally generated, possibly by energy discharge or a regulated pulse, or B. reflected from a hidden chamber facing inward toward a central cavity. Both scenarios require non-random internal geometry and potentially energy manipulation. Further complicating things is the repeated timing. The reflections happened during a specific moment in the 9-minute pulse cycle, right as the ultraviolet hotspots activated. The connection is hard to ignore. UV modulation, subsurface cooling, and now internal optical alignment. 3 events, 1 object, 1 rhythm, and still, no natural body has ever behaved this way. The fact that this reflection pattern could only be confirmed via triangulation, using multiple observation points across the planet, underscores how subtle but real this phenomenon is. We are not looking at a random glint. We are looking at a light path, trapped, bounced, and released from within an object that shouldn't even be hollow. And if light can move through it like that, what else can? As new images poured in during the early hours of December 2nd, 2025, astronomers across 3 continents began asking the same question. Where did the coma go? For weeks, 3i Atlas had exhibited what many assumed was a standard cometary coma, a diffuse cloud of gas and dust that typically surrounds a nucleus as it interacts with solar radiation. It was faint, asymmetrical, and extended outward in irregular pulses. But by the time mid-December began, that feature had quietly vanished, and in its place, something cleaner, sharper, and far more structured had emerged. In the most recent composite images from the solar orbiter's METI coronagraph, the object now displays a distinct hard edge, unlike anything associated with comets, asteroids, or even interstellar debris. There is no halo, no gas plume, and no tail. Instead, there's an unmistakable boundary layer, precisely shaped, sharply defined, and consistent across multiple wavelengths. This discovery was first confirmed by the Canada-France-Hawaii telescope using polarization filters. The result? A sudden and complete collapse of the previous light scatter pattern that had once given the object a dusty, nebulous aura. In its place, a boundary emerged that was non-fractal, geometrically smooth, and even angular at certain points, indicating that whatever surrounds the core now is not expanding gas, but something solid or at least fixed in structure. This is where the findings take a dramatic turn. Cometary comas are caused by outgassing. As sunlight heats the volatile compounds inside a comet, jets of gas erupt from beneath the surface, dragging along small particles of ice and dust. These form a luminous halo that extends thousands of kilometers, often evolving chaotically based on the object's rotation and trajectory. But that's not what's happening here. Analysis from the Stratospheric Observatory for Infrared Astronomy, SOFIA, showed no signs of sublimation, no trace gases, and no kinetic dust movement beyond a few localized flickers, which by the way were synchronized with the object's 9-minute internal modulation pattern. The implication is clear. 3i Atlas has shut down its outgassing, or it never had any to begin with. Instead, astronomers believe they are witnessing the emergence of a static outer shell, possibly replacing what was previously mistaken for a coma. This shell appears to be forming a layered buffer between the internal object and interplanetary space, almost like a sheath or exoskin. But that leads to a deeper and more unsettling question. Was the coma ever real? Or was it an adaptive camouflage layer, now retracting or reorganizing into something more defensive, or more deliberate? The James Webb Space Telescope recorded spectral data across the 2.5 to 12 micron range, revealing a steep drop in surface emissivity around the object's new boundary. This drop cannot be explained by any known natural material behavior. The readings instead resemble synthetic composites, or engineered shielding, designed to absorb and deflect rather than emit or scatter light. Meanwhile, ground-based observers using laser interferometry noted something even more bizarre. The object's outer boundary pulses, but not outward. It pulses inward, as if breathing or recalibrating. This observation echoes the early December findings from Chapter 1, where the outer shell appeared to fold inward rather than break apart. With the coma gone, that process is now clearer than ever. The object is no longer surrounded by chaos. It is surrounded by coherence. It's almost as if 3i Atlas has completed a phase change, from an open system to a closed one, from an emissive object to a reflective one. One astrophysicist from the European Southern Observatory phrased it best. This is not a loss of material, it's a change in posture. Comets decay, shells form. Only one of those processes involves order, and in this case 3i Atlas isn't collapsing, it's closing itself off. Which leaves us with a final pressing thought. If it's no longer releasing anything, then what is it preparing to keep in? Or perhaps, what is it preparing to let out on its own terms? By the evening of December 2nd, 2025, what had begun as speculation among astrophysicists had solidified into a repeatable data pattern. 3i Atlas is changing shape, morphing, not randomly, but in direct alignment with solar intervals. That word, morphing, is not used lightly in astrophysical circles. Celestial bodies may fracture, erode, disintegrate, or spin, but they do not typically morph. To morph suggests a progressive, deliberate, and rhythmic transformation of physical form. And yet, that is precisely what this object appears to be doing, not once, not twice, but in measurable cadence with the fluctuations of solar radiation pressure and particle flux. It began with observations from SOHO's LASCO C3 coronagraph, which noted faint but consistent shape alterations in the silhouette of 3i Atlas every 66 minutes, a time interval that, at first, seemed arbitrary. But when mapped against the Sun's Type 3 radio burst schedule and local proton flux variability, a chilling correlation emerged. Each morphing event occurred just minutes after spikes in solar energetic particle, SEP levels, particularly during short, high-energy solar fluctuations that are typically dismissed as space weather noise. Why would this matter? Because no natural object has ever demonstrated a structural response that correlates so tightly to the Sun's micro-output patterns. The SEP spikes being referenced here are not massive solar flares or coronal mass ejections. They are minor modulations, small and rapid energy pulses detectable only by high-resolution space weather instruments. And yet, 3i Atlas is reacting to them, as if it's listening or syncing with something embedded in the solar environment. To verify this, the research teams at Goddard Space Flight Center and JAXA's Solar Sea mission overlaid shapeshift timestamps with real-time solar data. The match rate? Above 92%. That's not noise. That's a response loop. So what's changing? The object isn't expanding or crumbling. It's reconfiguring. Edge contours shift inward or outward by meters at a time, following geometric curves that suggest flexible outer plating or membrane-like movement. Spectral analysis during these moments reveals temporary distortions in ultraviolet and infrared bands, consistent with material repositioning rather than gas movement or debris shedding. And here's the most perplexing part. The morphing occurs more quickly and precisely when the SEP spikes are brief and sharply defined. When solar output is erratic, the object remains mostly still. But when the Sun produces clean, defined pulses of energy, 3i Atlas responds with equal clarity, its outer geometry tightening, folding, or opening in perfect sync. This isn't passive absorption, it's behavioral coupling. The emerging hypothesis is both simple and terrifying. 3i Atlas is tuned, engineered or naturally adapted to solar rhythms, not just gravitational or orbital mechanics. Think about what that implies. If an object from interstellar space is adapting to the Sun's lesser-known energetic cycles we ourselves only recently learned to detect, then either. It was designed with prior knowledge of these intervals. It possesses internal systems capable of sensing and reacting to solar information in real time. One points to foresight, the other points to technology, and in both cases the morphing is not reactive in the way rocks heat and cool, it's deliberate and selective, as though 3i Atlas is using the Sun as a timing mechanism, or even a trigger. Some are now asking, is the Sun acting as a communication relay? Or worse, has something inside 3i Atlas been waiting for these intervals to begin a process we're only now witnessing in slow motion? The symmetry is undeniable. The rhythm is measurable. The silence from official agencies, deafening. Whatever this is, it is not adapting to Earth. It's adapting to the Sun. And that means its intended trajectory, its true purpose, was always meant to pass through our system, only when the solar signal said the time was right. In the early observational hours of December 2nd, 2025, a new layer of complexity emerged, one that shook even the most seasoned astrophysicists. Across 3 observatories, in 3 different countries, astronomers reported a disturbing trend. The morphological shifts of 3i Atlas, its changing shape, appeared to correlate with the location of Earth-based telescopes observing it. This was not a one-time fluke. It began with the European Southern Observatory, ESO, in Chile, where a group of researchers noticed that during their extended 40-minute tracking session, 3i Atlas displayed subtle oscillations on one edge of its outer structure, small movements along the equatorial band, captured with precision thanks to adaptive optics. When their session ended and the object rotated out of ESO's optimal view, those oscillations ceased. That alone could have been dismissed, but simultaneously, a telescope array in South Korea, which had just acquired line of sight on the object from a different angle, captured a new series of structural shifts, this time along a polar axis, in areas that had previously remained stable. The shifting wasn't random, it was observer-specific. When analysed by a collaborative team from the SETI Institute and the Paris Observatory, the data revealed a consistent relationship between which part of the object was being observed from Earth and where the shape change occurred on its structure. It was as though the object knew where it was being watched and changed shape where it was most visible. That's not just improbable. That's something we associate with reaction, with awareness. Let's break this down using known physics. No natural object, especially at the distance 3i Atlas resides from Earth, should have the sensory feedback required to detect ground-based optical observation. Our telescopes operate by collecting passive light. We do not emit lasers or active probes. There is no reason 3i Atlas should know where on Earth it's being watched from, let alone respond to that attention with shapeshifts that track our gaze. Yet, that is what the data shows. To test this hypothesis, researchers at the Subaru Telescope in Hawaii launched a 9-hour experiment in coordination with the Gran Telescopio Canarias in Spain. Each observatory was tasked with maintaining a fixed observational window and tracking any observable deformation in the object's edge profile. Within 27 minutes, the teams began to notice a mirrored pattern. As the Canary Islands track the western limb of 3i Atlas, small surface folds began to emerge, resembling an accordion-like ripple effect, roughly 70 meters across. Meanwhile, as the Hawaiian team focused on the object's southeastern quadrant, thin edge flickers, not bright enough to be reflections but not dim enough to be dismissed, began pulsing every 4.5 minutes, aligned with their telescope's viewing vector. Neither of these effects were present in the baseline imagery collected hours prior. They occurred only while being watched. This led to an even deeper question. Are we interfering just by observing? Or has 3i Atlas been designed to respond to attention? The philosophical implications aside, the scientific conclusion is staggering. In behavioral biology, animals exhibit gaze detection, the ability to sense when a predator or rival is looking at them. This often triggers self-defense behaviors, camouflaging or fleeing. What 3i Atlas is doing looks eerily similar, though expressed in material geometry rather than motion. Could it be that the object is sensitive to electromagnetic leakage from Earth-based systems, computers, thermal imaging, even our radio chatter? Or, and this is the theory gaining momentum, does it possess a passive observation monitoring system capable of detecting changes in photon angle density from Earth-based optics? In other words, has it been watching us watching it? The implications go far beyond astronomy. This shifts the object from being a passive traveller to an interactive presence, aware, adaptive, and subtly synchronized with our attention. If true, this means that every telescope aimed at 3i Atlas is not just recording it, but also provoking it. And as more nations aim their highest resolution instruments toward it, what happens when all eyes are on it at once? We may soon find out. In the quiet precision of orbital mechanics, a change of 0.03 degrees may sound insignificant, an imperceptible tremor against the backdrop of vast cosmic motion. But on December 2nd, 2025, when 3i Atlas's central symmetry axis shifted by exactly that amount, it sent shock waves through the astronomical community. Because this wasn't just a drift, it was a tilt, subtle, deliberate, and aligned with the object's most geometrically balanced plane. And it came after weeks of static orientation, despite high-velocity movement through the inner solar system. Let's define terms first. The symmetry axis of a body like a comet or interstellar object is the central line around which its geometry appears balanced. In natural objects, especially tumbling asteroids or outgassing comets, this axis is often erratic or unstable. But since its discovery, 3i Atlas has displayed an uncanny level of structural equilibrium. It maintained an almost perfect axial stability. No tumbling, no chaotic precession, and no erratic torque responses, even as it accelerated under solar radiation and gravitational influence. Until now, on December 2nd, high-resolution telemetry from the Very Long Baseline Array, VLBA, indicated that 3i Atlas had rotated its primary symmetry axis by 0.03 degrees relative to both its orbital vector and solar angle. To the untrained eye, this may seem like background noise, but when tracked across observational data from 18 separate instruments, including the James Webb Space Telescope, the Solar and Heliospheric Observatory, SOHO, and the Lick Observatory's Adaptive Optics System, the numbers all confirm the same directional drift. More critically, the tilt occurred in a time-locked window of 17 minutes, with no precursor acceleration, no external forcing event, and no radiation spike that could account for a natural torque application. In short, the object rotated itself. But why 0.03 degrees? Why not more? This is where the data gets strange. The direction of the tilt aligns 1.1 with Earth's ecliptic observation plane, as though the object was optimizing its posture not for orbital balance, but for visibility. This theory is further supported by spectral albedo mapping from the Atacama Large Millimeter Array, ALMA, which recorded a brief increase in reflectivity symmetry after the shift. The object's opposing hemispheres, which previously showed mild variation in emissive output, became almost identical in structure and energy distribution, suggesting the tilt brought both sides into phase alignment with Earth's most frequently used observation windows. That's a behaviour we typically associate with signal dishes, adaptive optics, or rotating satellites, not with comets. And here's another clue. The rotational correction didn't just happen once. Over the next 6 hours, microtilts totaling an additional 0.05 degrees occurred in 2 follow-up intervals, both perfectly synchronized with Earth-based deep field imaging sessions scheduled through the International Virtual Telescope Alliance. Every time large groups of telescopes began viewing it, the object fine-tuned its axis slightly closer to optimal exposure, almost like it was positioning for clarity. Now, let's rule out the natural causes. Gravitational perturbation? Not possible. No large body was nearby. Solar torque? Unlikely. Radiation pressure at this distance could not produce such a discrete, short-duration angular response. Outgassing recoil? Not supported. There's no evidence of volatile discharge or thrust-like activity. What we're left with is the one explanation astrophysicists are reluctant to state publicly: internal actuation. Some mechanism inside 3i Atlas is capable of controlling its orientation with exquisite precision, and it is choosing to tilt in ways that enhance its visibility to Earth-based systems. We're no longer looking at a drifting rock. We're watching an object that, despite travelling at extraordinary velocity, is making fine adjustments in its exposure angle consistent with active posture control. The margin is razor thin, the motion is barely detectable, but the math is consistent and the repetition is undeniable. This object is behaving as if it wants to be seen, clearly, symmetrically, and on its own terms, and the more precisely we look, the more precisely it seems to respond. This isn't just a tilt, it's a signal, with geometry. On the morning of December 2nd, 2025, a new anomaly emerged, not from shape, motion, or trajectory, but from light itself. Spectral scans of 3i Atlas conducted by the James Webb Space Telescope, JWST, alongside ground-based absorption studies from Mauna Kea, revealed a development that stunned the scientific community. The object's absorption profile had changed, in a way that could only be explained by one thing: a reorientation of its material composition. Let's begin with the basics. When light from a star or the sun passes through or reflects off an object, certain wavelengths are absorbed based on the chemical and structural makeup of that object. This creates a distinct pattern called a spectral fingerprint. It allows astronomers to infer surface materials, internal temperatures, and energy behavior. For 3i Atlas, those spectral fingerprints had remained largely stable for weeks, showing a consistent absorption pattern in the near-infrared and mid-infrared bands, with occasional narrow-band dips in the ultraviolet range. These dips suggested either a reflective composite surface or an extremely low outgassing mineral body. But suddenly, on December 2nd, those dips began to shift, and not randomly. At precisely 0517 UTC, the absorption trough at 6.2 microns, normally associated with silicates or carbon-rich dust, broadened by nearly 9%. At the same time, the dip at 3.4 microns, a signature often tied to synthetic polymers and carbon-hydrogen chains, narrowed and deepened. The implication: parts of the surface reoriented themselves in relation to the incoming solar spectrum. In other words, the object did not change what it was made of. It changed how those materials were positioned, and that changes everything. You see, no known comet or asteroid adjusts its orientation at the molecular or surface structural level. At most, dust can scatter, melt, or fragment. But the data from JWST and Mauna Kea showed something far more refined. Specific absorption zones were either dampened or amplified depending on the object's exposure to sunlight and telescope angle. This is not normal. Dr. Hannah Mori, a spectrographic analyst at the Royal Astronomical Society, described it this way: "It's like the object is rotating internal panels or plates to change how light interacts with it, not to cool down or protect itself, but to curate its own spectral response, almost like it's choosing how it wants to be seen, selecting which wavelengths to let through." This language, choosing, is controversial in scientific circles, but the evidence is forcing researchers to reconsider their vocabulary. To dig deeper, a coordinated experiment was launched between ALMA and the Infrared Telescope Facility, IRTF, in Hawaii. These facilities focused on the object's absorption changes over a 90-minute observation arc, cycling through thermal, visible, and infrared scans every 14 seconds. The result? A pattern emerged. Every 9.2 minutes, the spectral absorption at 10.4 microns would flatten, then spike again, suggesting a rhythmic realignment of material layers just beneath the object's visible surface. This matched perfectly with earlier studies about internal modulations where time-staggered light curves suggested a core structure that flexes. Here's the game changer. If material is reorienting without the object itself rotating, we may be looking at a modular shell, layers or plates embedded with substances that can physically shift alignment beneath the surface. This is not outgassing. This is not natural melting. This is controlled material reorientation. The physics of such a mechanism would be staggering, requiring internal power sources, sensors, and localized heat regulation. And yet, we're seeing signs of it in real time, at a distance of over 200 million kilometers. So what does this mean? It means the object is not static. It is not even passively reflective. It is actively managing the way it interacts with the electromagnetic environment, possibly to evade, communicate, or adapt to conditions we don't yet understand. It's no longer enough to describe 3i Atlas by size, speed, or trajectory. We now must speak of it as a responsive system, a body capable of subtle but intentional shifts in its material state, driven by inputs we're only beginning to decode. What kind of object is that? Certainly not a comet, not a rock, not a fluke of nature, something else. For weeks, astronomers tracking 3I Atlas were fixated on a strange, counterintuitive phenomenon, an anti-tail. Unlike a conventional comet tail, which forms as dust and gas are blown away from the nucleus by solar radiation pressure and the solar wind, the anti-tail of 3I Atlas extended forward, along its direction of motion, toward the Sun, rather than away from it. This was already a rare and confusing structure, but on December 2nd, 2025, that feature vanished, and not gradually. It disappeared within 4 minutes. Observatories across the globe, Spain's Calar Alto, Japan's Okayama, Astrophysical Observatory, and multiple amateur telescopes across the American Southwest, confirmed the event. What had been a visible, high-contrast extension of material against the solar backdrop simply ceased to exist. Let's rewind. The existence of an anti-tail is not impossible. In some cases, particles released by a comet can form a trailing stream that appears to point forward due to the viewing geometry from Earth, but that relies on specific alignments and predictable dust behavior. With 3I Atlas, however, none of those criteria were met. Its anti-tail was persistent, geometrically aligned with its trajectory regardless of Earth's orbital position, and showed structured edges that shimmered in a way no known dust cloud would. It held its shape even through small course corrections and velocity changes, and now it's gone. So what happened? Here's what didn't happen. No solar flare or coronal mass ejection occurred during the window in which the anti-tail disappeared. Solar wind pressure, as measured by the ACE and DSCO-VR satellites, remained stable at the time. There were no spikes, drops, or disturbances that could strip away or disperse a tail that size. No collision or impact event was recorded near the object. The solar environment was quiet. The region was stable. There was no external force that could account for the vanishing of the structure. And yet, it's gone. Several theories were proposed within 24 hours. One of the more conservative suggestions was a rotational realignment, that 3I Atlas simply changed orientation, causing the anti-tail to become invisible from Earth. But that theory breaks down under scrutiny. Using spectral layering from the solar orbiter and multiple ground-based arrays, scientists confirmed that light previously scattered or refracted through the anti-tail was no longer being detected at any angle. The feature had not rotated out of view. It had ceased to exist physically. A more daring hypothesis comes from researchers at the University of Bern. The anti-tail was never made of loose particles. Instead, it may have been a dynamic field structure, something akin to a magnetic or plasma projection that held solar-charged particles in a rigid spatial configuration, like an antenna or shielding mechanism. If that sounds speculative, consider this. Right before the anti-tail vanished, high-frequency radio telescopes in Chile recorded a short frequency-stable burst at 1420 midesims, a band known for hydrogen emissions, and historically flagged in SETI projects due to its cosmic neutrality and efficiency. That burst lasted 2.8 seconds, originated from the object's vector, and stopped at the exact moment the anti-tail disappeared. Coincidence? Maybe. But now the discussion is shifting. Some believe that the anti-tail may have been part of an active energy management system, one designed to deflect solar radiation or manage electromagnetic exposure. Its sudden collapse could signal a transition into a different operating mode or even a system shutdown. Others think it was performative, a visible extension meant to mimic known comet behavior until it was no longer needed. Here's what remains undeniable. Whatever the anti-tail was, it was not governed by the solar wind. Its existence and disappearance defies standard astrophysical explanation. It behaved like a feature under internal control, one that appeared, held formation, and then disengaged on a timetable that had nothing to do with space weather. For an object millions of kilometers from Earth, that is unprecedented. And it leaves us with only one conclusion. 3I Atlas is no longer just unpredictable. It's now exhibiting selective, timed, and environment-independent behavior. The sky didn't erase the tail. The object did. After a brief but notable pause of nearly 11 hours, the pulsing behavior of 3I Atlas resumed on the evening of December 2nd, 2025. This would have been noteworthy on its own, given how previously rhythmic emissions had momentarily ceased. But what emerged next took the phenomenon into entirely new territory. The pulses returned, but this time they echoed from within. Let's start with what astronomers have been tracking for over 2 weeks now. 3i Atlas emits broadband pulses of electromagnetic energy, mainly concentrated in the VHF and UHF spectrums, at nearly predictable intervals. This is not typical behaviour for comets, asteroids, or interstellar rocks. These emissions are short, patterned, and oddly stable across multiple rotations. Normally, pulse events occur every 17 minutes and 8 seconds, a near-perfect harmonic interval. That pattern held until the early morning of December the 2nd, when the signal abruptly stopped. No interference, no drifting signal, just silence. That silence lasted 10 hours and 56 minutes. Then, at 1937 UTC, the pulses returned, but with a distinct second layer of signal not seen before. For the first time, high-resolution instruments began detecting internal resonance echoes, short, repeat signals that followed each main pulse by exactly 1.2 seconds. This new echo signature was picked up simultaneously by 3 deep-field monitoring systems: the LOFAR array in the Netherlands, the CHIME radio telescope in Canada, and the Parkes Observatory in Australia. All 3 recorded the same double signal structure: a strong primary burst, followed by a weaker, delayed repeat, consistently offset by 1.2 seconds, down to the millisecond. This is not noise. This is not reflection from space debris. This is internal echoing, a signature consistent with sound or signal reverberation inside a hollow structure. According to Dr. Lena Korik, a signal processing specialist at the European Space Agency, the 1.2-second delay corresponds to the time it would take for a signal to travel across a large enclosed volume, reflect off the opposite wall, and return. Her team ran simulations based on known materials and signal propagation speeds. Their early models estimate that such an echo delay would be consistent with an internal cavity roughly 200-250 meters in diameter, surrounded by surfaces dense enough to bounce a high-frequency pulse cleanly, without signal scatter or degradation. So what does this mean? It means the pulses are not just being emitted into space. They're interacting with something inside the object. This something is highly structured. The echoes do not vary in time. They don't warp under solar influence, and they repeat with each pulse in a stable feedback loop, as if part of a calibrated internal system. The implications are staggering. Echoes of this kind are not found in natural bodies. No comet, asteroid, or interstellar rock has ever produced a repeating pulse pattern with internal reverberations. Even the infamous Oumuamua showed no such features. This behavior aligns more with sonar systems, resonant chambers, or even engineered probes, where internal cavities play a role in stabilizing signals or regulating frequencies. One potential interpretation is that we're witnessing a diagnostic cycle, a system that sends out pulses and listens for echoes to detect changes in the internal structure, like submarine sonar pinging the hull. Another possibility, the object is mapping itself in real time, using harmonic pulses to maintain internal balance or recalibrate modular components. But the most unsettling theory? That the object is broadcasting information to itself, an autonomous system with internal feedback used for processing, steering, or even communication within nested structures. Regardless of the cause, the resumption of the pulses with echoes marks a turning point. It's no longer enough to say that 3i Atlas is emitting energy. It is now listening to its own emissions. It is responding, measuring, reverberating. The cosmos is quiet, but this object has sound. And the sound is coming from inside. On December the 2nd, 2025, the object known as 3i Atlas continued its slow descent toward the inner solar system. A striking inconsistency emerged, one that forced astrophysicists to reopen a question they thought was already settled. How much does this object actually weigh? The answer, it turns out, doesn't match the math anymore. Let's break this down. Mass estimates for interstellar objects are not directly measured by scales, of course. Instead, scientists calculate mass based on rotational dynamics, trajectory curves, thermal inertia, and more recently, gravitational microlensing effects. These calculations, while indirect, are generally reliable. especially when supported by weeks of consistent motion data. For the past 19 days, 3i Atlas had exhibited a rotational period of 9.73 hours, with a stable axial tilt and a precession wobble of just 0.009 degrees per orbit. Based on this motion, and how it responded to gravitational influences from Jupiter and the Sun, the estimated mass was placed at around 2.4 x 1011 kilograms, comparable to a mid-sized asteroid. But on the morning of December 2nd, the object's rotational velocity changed, and not subtly. High-resolution optical tracking from the Very Large Telescope, VLT, in Chile, and corroborated by radar imaging from Goldstone Deep Space Communications Complex, showed that 3i Atlas's spin slowed by 0.022 rpm over a period of just 36 minutes. That may sound small, but for an object of this estimated mass, such a change should require a significant external torque or internal mass redistribution. And yet, there was no torque, no jetting, no off-axis outgassing, no collision. The object simply slowed down. If the original mass estimate were correct, then conservation of angular momentum would demand an external force to produce this deceleration. But all observational channels confirmed no external force was acting on the object at the time. This left one troubling possibility. The object's mass is significantly lower than we thought. Researchers at Caltech recalculated the angular momentum loss and compared it to known cometary and metallic body behaviours. The numbers pointed to a revised mass estimate of no more than 7.11 1010 kilograms, less than a third of previous assumptions. The implications are serious. This kind of discrepancy suggests one of two things. The object is hollow. The object is actively redistributing internal mass in real time. Let's examine the first. A hollow object would account for the low inertia and rapid rotational variance. It would also align with the echo pulses detected earlier, supporting the idea of an internal cavity or framework. But a truly hollow natural body of this size would collapse under its own minor gravitational field, unless its structure was exceptionally rigid or artificially reinforced. Now the second option, active mass redistribution. This would imply internal systems, mechanical, electromagnetic or otherwise, shifting weights, modules or components to compensate for rotation or adjust to observational vectors. Some satellites and spacecraft use similar internal mass balances, but those are designed, and 3i Atlas was never meant to be. Or was it? To test both theories, a team at the University of Tokyo ran simulation models using assumed shell structures, layered rotating cores, and variable density materials. Only one model matched the observed slowdown, a lightweight outer hull with multiple rotating subsystems inside, capable of absorbing or adding angular momentum selectively. That's not a comet, that's a system. And here's the kicker, the object's overall trajectory did not change. Despite the shift in rotational energy, 3i Atlas stayed perfectly on course, as if course corrections were internalized, absorbed rather than reacted to. A naturally tumbling rock would have drifted. This one corrected. The conclusion is becoming harder to ignore. The mass of 3i Atlas is no longer behaving like a fixed quantity. It's behaving like a managed variable, a controlled parameter in a responsive object. It's not just the rotation that shifted, it's our understanding of what mass means in an object like this. 3i Atlas isn't just changing speed, it's changing the rules. At exactly 02:51 UTC on the night of December 2nd, 2025, a strange and seemingly contradictory observation began circulating between the world's leading skywatching facilities. The object known as 3i Atlas, which had already been exhibiting structural morphing, energy pulses and motion anomalies, was now visibly shrinking. But not in mass, not in energy, and certainly not in thermal signature. It was shrinking optically, but not thermally. Let's unpack that. Telescopes at multiple locations, including the European Southern Observatory, Mauna Kea, and the Canada-France-Hawaii telescope, began reporting a reduction in the object's apparent size across optical wavelengths. Specifically, high magnification tracking showed that the visual diameter of 3i Atlas had decreased by 13.2% over a 6-hour window. Now that kind of shrinkage might seem explainable. Maybe it's simply moving farther away. No, the object's distance from Earth was constant during that window, Its trajectory relative to both Earth and the Sun had been precisely plotted by ESA, NASA, and JAXA, and there was no sudden acceleration or change in orbit. Then maybe it was turning, rotating and presenting a narrower profile to our instruments? Again, no. Rotational data showed no realignment of the object's axis, or a shift in visible surface area that could account for such a significant drop in apparent optical size. Whatever this shrinking was, it wasn't rotational and it wasn't positional. But here's where it gets stranger. Infrared and thermal imaging from the Spitzer IR telescope and the Atacama Large Millimeter Array, ALMA, showed zero change in thermal output, none. The object continued to emit the same heat signature, uniform, high contrast, and with no drop in radiation across its known surface temperature zones. This means that, despite appearing smaller to our eyes and cameras, the object was radiating heat as if nothing had changed. That shouldn't happen. In physics, an object that shrinks in size, whether through material loss or contraction, should proportionally lose emissive surface area and therefore radiate less heat. But 3i Atlas wasn't following that rule. It looked smaller, but it stayed just as hot. This is the astrophysical equivalent of watching a campfire visibly disappear before your eyes, while still feeling the same warmth on your face. So, what are the theories? The first is optical occlusion, the idea that 3i Atlas might have deployed or engaged some form of visual masking, cloaking, or reflectivity adjustment that reduces its visible profile without altering its actual size. This isn't just science fiction. Many Earth-based stealth technologies function by minimizing reflection or redirecting light away from sensors. If a material could do that across multiple visual bands, it might explain the shrinking without thermal loss. The second theory is variable refractive geometry. Essentially, the structure of the object may be capable of altering how it bends or emits light, folding wavelengths away from direct view while still holding heat. Some animals in the ocean, like octopuses, can change shape and reflective quality simultaneously. Apply that concept to advanced materials in deep space, and the physics starts to check out. But the third theory is the most radical. Some physicists now believe 3i Atlas is employing a kind of optical compression field, not shrinking in the physical sense, but reframing its apparent volume, similar to gravitational lensing effects. This could result in smaller visible footprints while retaining original thermal emission, due to unchanged mass and energy density. If true, that implies this object isn't just morphing. It's controlling how we perceive it. We see less, but it burns the same. The question is, why? Could this be a defensive mechanism triggered by intensified observation? Could it be a transitional phase, part of some onboard system recalibrating for solar proximity? Or worse, could it be intentional obfuscation, meant to confuse or delay our understanding? All possibilities remain on the table. But here's what's clear. On December 2nd, 3 Atlas shrank before our eyes. But every thermal instrument, every infrared sensor, and every radiometric scan screamed the same truth. It didn't go anywhere. What vanished was just the image. What remained was the heat. And heat in space doesn't lie. As of the early morning hours of December 2nd, 2025, the most advanced telescopes across the globe are converging on one unsettling conclusion. 3i Atlas is not just drifting toward Earth. It is changing, methodically, rhythmically, and possibly on schedule. And now, with less than 2 weeks remaining before its closest approach to Earth's orbital shell, a new theory is beginning to circulate among astrophysicists, signal analysts, and even aerospace engineers. This could be structural recalibration. Let's be clear, this is not speculation pulled from science fiction blogs or conspiratorial circles. This hypothesis is rooted in pattern recognition, physics, and repeatable measurements. And now we have a final, converging question. Why would an object change this much, right before its flyby? In nature, objects entering the inner solar system are expected to respond to solar radiation, gravitational tides, or internal pressure buildup. These responses typically lead to cracking, fragmentation, outgassing, or disintegration. But 3i Atlas is not disintegrating. It is refining. Its light curves are smoothing. Its pulses are accelerating. Its symmetry is increasing. This pattern looks less like decay and more like preparation. At the JET, Propulsion Laboratory, Orbital analysts have simulated over 2,000 approach scenarios using updated telemetry from ESA and NASA. In over 97% of those scenarios, 3i Atlas passes within 0.037 AU of Earth. That's just 5.5 million kilometers, or about 14 times the distance to the Moon. Close, but not a collision course. Still, its proximity means it will intersect with multiple layers of Earth's electromagnetic field, radiation belts, and possibly even interact with ionospheric structures. If this object is artificial, or even semi-structured, then entering that complex magnetic environment could require reorientation, shielding adjustments, or even communication recalibration. Some researchers now believe 3i Atlas is engaging in just that, a final systems check, a modular alignment of structural components, a recalibration of orientation relative to Earth-based observers. We explored how its structural shifts appear to track Earth-based observation points. This suggests not just passive movement, but responsive adaptation. Think about that. We're no longer watching an object behave as a mere wanderer of interstellar space. We are watching a system, one that adapts its mass balance, optical profile, pulse timing, and geometric structure, all just days before it enters the region where Earth's instruments are most sensitive. At the University of Vienna, a working group has labelled this phase a pre-flyby stabilization pattern. They propose that 3i Atlas may be minimizing its visible footprint while maximizing signal fidelity. In their simulations, the object compresses its form, equalizes temperature gradients across segments, and reduces radar reflectivity by up to 80% through geometric alignment. Now here's the most concerning part. Every change we're seeing today is reversible. Nothing is being destroyed, no energy is being lost, everything is being redistributed. In aerospace terms, this would be known as a non-permanent morph, a structural configuration meant to adapt to incoming forces, then restore after the phase completes. That is not comet behavior, that is vehicle logic. Could this be how a probe reorients itself before slingshotting around a planet? Could this be shielding optimization, or a deceleration maneuver hidden in the math of form? Or could it be a display, a carefully timed performance only visible when Earth is watching? We don't know, but what we do know is this. Every one of these shifts, optical, thermal, structural, and rotational, has aligned in time, not randomly, not chaotically, but with clockwork precision. This object isn't losing control, it's taking it. As Earth approaches, 3i Atlas is doing exactly what an intelligent system would do: prepare.